Hi, welcome to Advanced Math, Chapter 12 on Vectors, Part B, page 4. Continuing, we're looking in the previous page at an example like this where we have a vector u and we can write it as the sum of two perpendicular vectors ux and uy that are parallel to the x and y axes respectively. Now, when we do this, what we're getting, of course, is a right triangle. Now, if we want to introduce the angle, so that's up until now, we've been looking at these arrows and saying, well, this vector is about yay long, and it goes to the upper right or the upper left, which is okay, but it's not very precise, as you probably are aware. So one of the ways, of course, for specifying a direction of something that we're familiar with is the angle. And the angle shown here is the same way we would measure an angle in the unit circle, counterclockwise from the positive x-axis. So, well, that's also the angle of one vertex of this right triangle. Now, we know from SOHCAHTOA that the cosine of that angle theta would be adjacent over hypotenuse. And in this particular case, the adjacent side length is the magnitude of component vector ux. So here's ux, and here we're saying the magnitude of that, that means the length of that vector. And the hypotenuse on this triangle is vector u, or more properly, the length or magnitude of vector u. So the cosine of that angle is equal to the magnitude of vector ux divided by the magnitude of vector u. Now, if we want to figure out the length of this component ux, we can just do simple algebra on that equation and find that the magnitude of ux is going to be equal to the magnitude of vector u times the cosine of theta. So again, this is the length of our vector, the magnitude of vector u, times the cosine of the angle. So it's very straightforward. The length of the vector, the magnitude, times the cosine of its angle. And if we want the magnitude or the length of vector uy, it's going to be exactly the same form, except we would be solving for the sign, because ui is the opposite side. So the magnitude or length of uy is going to be the magnitude of vector u again times the sine of the angle. So now we've got a way for any vector, if we know its angle, we can come up with its component vectors in the x and the y directions. And when you have the component lengths, the length of vector ux and the length of vector uy, um, those two lengths or numbers can be written as an ordered pair, sort of like a coordinate pair, but they mean those component lengths of a vector. And when you do that, you write it with the angle brackets like this. So here is a way of writing or describing a vector in terms of its horizontal vector component and its vertical vector component, ux and uy, the magnitudes or lengths of those vectors. And we write it inside the angle brackets to say, hey, this is not a point, this represents a vector, which is a slightly different kind of thing. So in other words, a vector 4, 3, you wouldn't go and plot that at location 4, 3 on a grid. Vector 4, 3 has no location. This is meaning a quantity that has a direction and a size. And the direction of this vector in component form is determined by the ratio of these two components. It's kind of like a slope. And the magnitude of the vector is determined by the size of these numbers, the magnitudes of the numbers. So you could have like 40 comma 30 would be in the same direction as 4 comma 3, but it would be 10 times longer. Alrighty. Now, if we have vectors in component form, is there a way to add those two vectors together that makes sense? And so what this diagram is doing is kind of showing how this is actually possible to do. So we've got a vector w that's equal to the sum of vector u and vector v. And for vector u and vector v, we can write out their component vectors. Vector u's component vectors are a and b, and vector v's component vectors are c and d. And vector w's components are f and e. Okay, so because all the component vectors are parallel to the x and y axes, we can easily add them together because the sum of those vectors, like if we look at vector E, that's equal to A and C. added together. And we can add these vectors together as vectors to be head to tail, and they would be equal in length to this vector and in the same direction. We can also think of this as just adding their magnitudes. Because they're parallel, we can add the magnitude of A, the length of A, and the magnitude of C, or the length of C, and that length should equal the length or magnitude of vector E. And so one way of writing that is to just say that E is equal to A plus C. And in a similar vein, we could say that F, that vertical component here, this vector F is equal to the sum of B and D. So F is equal to B plus D. Now, if we want to talk about this in component form, vector W, which is components E and F, E is the horizontal or X component, and F is the vertical or Y component. It's in X and Y order. That E component, we've already figured out, is equal to A plus C. And this F component here, we've already figured out is B plus D. So the punchline is, if we have vectors U and V that are in component form, A and B, just numbers. So this is a vector notation, A comma B. Vector U has components A and B. And if we add vector U to vector V, which has its components C and D, all we need to do is add the U vector's X component to V vector's X component, so A plus C. That becomes the first component of the resulting sum. And then the Y components of U and V, B and D, get added together, and that becomes the Y component of the W vector. So it is really straightforward adding vectors in component form. In fact, it's easier than doing it graphically. You don't need to have any artistic talent whatsoever. You just need to be able to add numbers. It's really nice. Super, super nice. Okay, I think, yes, that's the end of the page. Okay, next page, we're going to be doing some examples of simple arithmetic on vectors in component form coming right up.